This is the second in my series on the equations of motion. In my first video, we looked at the derivation of the equations, and now I'm going to look at the scenarios that there could be in the use of these, remembering that this is all about situations where the acceleration is constant. So, possible scenarios. The first possible scenario is something falling under gravity, let's say. So your initial conditions here, we're going to say it's going to start from rest, and its acceleration is going to be gravity. So this is, for example, you start your stone here and you drop it. So there's your first scenario, falling under gravity. Your second scenario would be something projected vertically against gravity. So again, you're going to have some initial velocity because it's being projected. The acceleration here is minus g, and that's because your object is going up, but of course g is acting the opposite way, and of course you would expect this thing to stop at the top, so you might say its final velocity is v. Then our third scenario, we've done falling under gravity, we've done projected vertically against gravity. Our third scenario would be projected horizontally. Now, of course, if we're going to do that, we're going to have to be at some height. So you're going to have a cliff, perhaps, and you're going to project horizontally. So there's your horizontal velocity. Now, you're almost certainly going to be interested in how long it takes to get to the ground from some height, the height of the cliff, and how far it goes horizontally before it lands. So here you're going to be looking at both the horizontal and the vertical motions. You're going to have to consider those separately. But horizontally, there is no acceleration. We're ignoring air resistance because we're physicists and we can do that. And vertically, the acceleration again will be gravity, because as it falls, its velocity increases. So gravity is acting positively, whereas here, as it rises, its velocity decreases. So clearly it's a negative acceleration. So those are our three scenarios that we need to deal with. The fourth scenario, which we don't so much need to deal with, but we're going to do anyway, is projected at an angle to the ground. And so here you have your ground. Let me try to do that horizontally. And you project with a velocity at some angle. And again, you're going to have to consider your horizontal and your vertical. But here you're going to have to resolve your velocity, your initial velocity vertically, and your initial velocity horizontally. So you've got u sine theta and u cos theta. U cos in this direction, you sign in that direction. So those are your 4 scenarios. Now let's look at those scenarios in turn. So let's take something falling vertically under gravity. So our first scenario, falling under gravity. Let's take an example of this then. So let's say we have a stone which is dropped into a well and it takes 3.0 seconds to hit the water. G is 9.81 meters per second squared. And let's work out, to start with, how deep is the well? By which I mean how far is it to the water? So, what do we know? We know the initial velocity is 0 because it's just dropped, it's not thrown. We know the acceleration is 9.81 meters per second squared. And we know the time is 3.0 seconds. And I'm also noting I've got 2 sig figs here, I've got 3 here, so my answer will be to 2. So, how deep is the well? Well, we want an equation of motion which connects the displacement with the initial velocity, the acceleration, and the time. So, I would say S equals ut plus a half at squared does it for me. I know that u is 0, so that simplifies things nicely. Plus a half times 9.81 times 3 squared. That gives me 44.15, but that's 4 sig figs. I can only have 2, so it's 44 to 2 sig figs. Then let's consider how fast it was travelling. Or words to that effect. So, what do we know? Well, we know the initial velocity is 0. The final velocity we're looking for. The time is 3 seconds, 3.0 seconds. And acceleration is still gravity, 9.81 meters per second squared. I want v, I've got u, a, and t. What am I going to do? V equals u plus at, of course. And if I stick in my numbers, 0, 9.81, 3, I'm going to get 29.43 out of that, but 2 sig figs, 29 meters per second to 2 sig figs. So, there's an example of our first scenario, nice and straightforward. Let's then consider firing something vertically upwards. This is our second scenario. not the best syntax in the world. Projection vertically upwards. I was going to write that again, that's what I would write. So let's consider another stone. Maybe it's the same stone. A stone projected vertically upwards at 40 meters per second. Pause there for a moment and think, that's very fast. So this is being fired mechanically. This is not someone throwing this by hand. So again, gravity is minus 9.81 meters per second squared. Why is it minus? Because as it goes up, it slows down. We're taking up as positive here. So let's ask ourselves, how high does it go? How about that? The maximum height attained. So what do we know? Well, we know the initial velocity is 40 meters per second. We know when it gets to its maximum height, it will stop. So we know the final velocity in this journey is 0. We know that the acceleration is minus 9.81 meters per second squared, and we want to know s. So we've got v, u, a, and we want s. How about v squared equals u squared plus 2as? We've got 0 equals u squared. Well, there's 40 squared, 1600. Minus 2 by 9.81 by s, which gives us s to be minus 1600 over minus twice 9.81. That's going to give us 81.5. And if we look at it, we've got 2 sig figs here, so that's going to be 82 meters to 2 sig figs. So that's nice and straightforward. How about we find out how long it takes to come back? Let's call that time in the air. Well, that's going to be the time to go up plus the time to go down, isn't it? So the time to go up, what's that going to be? Well, we know we have initial velocity of 40 meters per second, acceleration minus 9.81. We know the velocity will be 0 at the top. So how about v equals u plus at? I'm going to work horizontally as far as I can here to allow me to do all of this in one. So we know 0 is 40 minus 9.81 times t, which gives us t on the way up to be 4.08 seconds. Now, if we wanted that as our answer, we would write it as 4.1 seconds, but we don't want that. And we're not going to round just yet because we don't round in the middle of the calculation. So time on the way down then, well, what do we know? We know our initial velocity, it will start at 0 meters per second. We know it will travel 82 meters. So if we said s equals ut plus a half at squared, now This is displacement, and we said up was positive, and this is coming down, so that's minus 82. U, of course, starts off at 0 at the top, minus a half by 9.81 times t squared. And that then gives us a t of 4.08 seconds, which is no coincidence. The time on the way up and the time on the way down, they're going to be the same. And so the time of flight here, if you want to call it that, the time in the air, is 4.08 times 2, which gives us 8.2 seconds to 2 sig figs. So you could have just worked out the time on the way up and doubled it. But I wanted to illustrate that the two were the same. And then finally, how about the velocity on its return? Well, we know it starts off at 0 meters per second at the top. So we have u equals 0, a equals minus 9.81 meters per second squared, because it's still in that negative direction. And we know it spends 4.01 seconds doing it. Sorry. So if we used v equals u plus at, we get v to be minus 40 to 2 sig figs. Notice how the maths takes care of you. If you're careful with your signs, your answer will be correct in terms of its direction. So there's your second scenario. Our third scenario then, projecting the thing horizontally, the same unfortunate stone. Okay, so let's say we have a cliff 100 meters high. Let's say we project horizontally at 10 meters per second. And we're going to want to know how far from the base of the cliff the stone lands as part of our question. So let's say our first part of the question, time of flight. How long does the stone spend in the air? Well, ask yourself, what's the limiting factor here? Hopefully you'll see that the time of flight is the time it takes the stone to get from here to here. Hopefully a moment's thought will tell you that it doesn't matter how fast this is. That's got nothing to do with how long it takes to cover this distance. It doesn't matter whether this is dropped from here or whether you fire it out of a gun and it's doing 900 meters per second horizontally. The two will hit the ground at the same time. They will fall this distance in the same time. Assuming there's no resistance, of course. In the real world that isn't the case. But this is our cliff in a vacuum because we ignore air resistance, because we're physicists and we can. So the time of flight. This is the time to fall 100 meters under gravity. So we consider our vertical motion. Remembering we have to consider both in this scenario. So u equals 0 vertically. Let's make that uv. A is 9.81 because the velocity is increasing with time. And we want to know the time to fall 100 meters. Now, of course, you could say acceleration is negative because it's becoming more and more negative velocity as it falls, and therefore the displacement is also negative. So both of these would be negative, or in my scenario, I've decided I'm going to call them positive because it doesn't make any difference to me because they're either both positive or both negative. But let's say then S equals ut plus a half at squared. We've got 100, u is 0, plus a half by 9.81 by t squared, which gives us t to be 4.5 seconds. Then ask ourselves, what is x? How far does it travel from the base of the cliff before it hits the ground? Well, of course, x, that is the horizontal displacement during the time of flight. So, what do we know? Well, we know that the initial velocity is 10 meters per second. We know the acceleration is 0 because we ignore air resistance. So we know it's going to do 10 meters per second for 4.5 seconds. And so x will be 45 meters. Final question, final part of this question then, for which I'm going to need another sheet. Final part of the question then, what is the velocity on impact? Now, remember this is a vector. So, consider the vertical motion, consider the horizontal motion, consider the direction. So, horizontal velocity, well, that is 10 meters per second, it always was. There's no acceleration horizontally. The vertical velocity is u plus at, of course, which is 0 plus 9.81 times 4.5. So, well, 4.51 actually it was. So that gives us a vertical velocity of 44.3 meters per second. So now we have 10 meters per second that way. .3 meters per second that way. That's our resultant. That's our angle. So V then is the square root by Pythagoras of 10 squared plus 44.3 squared. And the angle, of course, is the inverse tan of 44.3 for 10. So if you do the little bit of arithmetic there, you'll get 45.4 here, so there's 45 to 2 sig figs. And you'll get 77 degrees to 2 sig figs there. So let's look at our final scenario then, projecting at some angle. So let's say we project something at an angle of 30 degrees to the horizontal at 900 meters per second. So we want to know the maximum height attained. We want to know the time of flight. And we want to know the range. We could also be looking at the velocity on return, but I'm just going to do these three here. So, looking at our first scenario, first part of the question rather, the maximum height. This is all about the vertical motion. And so we want to know our initial vertical velocity. And we know, of course, when it gets to the top, it's going to stop. And we know the acceleration will be minus gravity, because as it goes up, it slows down. And we want to know the vertical displacement under these conditions. So, what is our initial vertical velocity? Well, here we have 900 meters per second. This would be the vertical component of the 900. This would be the horizontal. You can see that vertically, you would say the sine of 30 would be uv over 900, and so uv is 900 sine 30. And by the same process, your horizontal is 900 cos 30. And we're going to need that later. So, just a reminder there on the resolution of vectors. So we have 900 sine 30 here. So we want S, we've got V, U and A. So we would say, sensibly I think, V squared equals U squared plus 2AS. V we know to be 0, U we know to be 900 sine 30, which is a half, of course, so that's nice and simple. Squared minus 2 by 9.81 times S. So we end up taking this over here, it becomes negative, divided by minus 2 times 9.81, and we get a height attained of 10,321 meters, which is three significant figures, 10.3 kilometers. The second part then, the time of flight. Let's look at that. So our time of flight. That is, of course, the time it takes in the air. So that's twice the time to the maximum height. So we would say vertically u equals 900 sine 30 degrees meters per second. V, of course, is 0. A is minus 9.81 meters per second squared. And we want to know the time. So, how about V equals U plus AT? T then is V minus U over A. And that gives us V is 0 minus 900 sine 30 divided by 9.81. That gives us 91.74 seconds, which is 91.7 seconds to 2 sig figs. Sorry, it's 2 times that. .7 seconds. The final part then, part 3, the range. And of course, in this case, what we mean by range is the distance travelled horizontally during the time of flight. So, we're looking at the distance travelled horizontally, so there's no acceleration. We have our velocity, initial velocity, which is the final velocity, because it doesn't change because there's no acceleration. And that, of course, is 900 cos 30 degrees, because the horizontal, so the vertical was 900 sine 30. So, S equals ut plus a half at squared, where A is 0, so S equals ut, which equals 900 cos 30 degrees times the time, which was 91.74, and that gives us 71.5 kilometers.